Hi. So I'm just going to talk quickly about matrix transformations because it's a question that's come up in one of my tuition sessions. So I thought it would be a good idea to just run through some basic principles and then to apply those principles onto an exam question. So matrix transformations. Assuming you know all about matrix algebra, then transformation matrices are special matrices that cause an enlargement or a stretch or a rotation or some form of reflection on a coordinate or a set of coordinates. So if I have an example transformation matrix R, and that's just arbitrary A, B, C, D. Then if I have a random matrix, so I'm gonna call this random matrix V, and I'm gonna give it x naught and y naught. The whole point of this transformation matrix, so that is my transformation matrix, is to put a stretch or some sort of rotation or some sort of reflection on this matrix V. So algebraically, I could write R dot V, and that will give me some version of V, which has either been rotated, or it has been enlarged, or it has been reflected. Okay, so this is my way of representing a rotation, an enlargement, or a reflection. And I'll just highlight those in blue. So rotation, enlargement, and reflection. Okay. There are two things that you should really understand and use when talking about matrix transformations, especially with enlargement or stretch matrices. The first thing is the determinant. So the determinant is given as det of my matrix equals the diagonal, the multiplication of the diagonal, take away the multiplication of the second diagonal. So in this case, it would be AD minus CB. And det R actually gives me the scale factor, or rather, importantly, the area scale factor. Now, this is very important, the fact that I've written an underlined area. Okay, so when you work out the determinant of any transformation matrix, you are working out the area scale factor of that transformation. That is very important. And I'm going to just box that. Oops. I'm just going to box that in red because I'm going to write another thing here. The other thing you should know about is the use of images. Okay, so the images of unit points or unit coordinates. So on a Cartesian grid in x and y, so that's the y-axis and that's the x-axis, and this is the origin here. And I'm going to call that, that's one, that's one, that's two, three, four. I'm only going to do this in the positive axis. And here we have 1, 2, 3, and 4. Okay. In order to describe what a transformation matrix is doing, we use images, and that's the same for stretches, rotations, and reflections. Images enable us to describe exactly what a transformation matrix is doing. The unit images are 1, 0. So I'm going to denote this with a green arrow, and 0, 1. So over here, that would be written as 0, 1. If you think back to vector notation, the number at the top of the 1 by 2 column vector is I, which stands for an increment in the x direction, and j, which stands for an increment in the y direction. So over here, it's going to be, I've gone 0 in the x direction, but I've gone 1 upwards. I've gone positive 1 upwards. So that's my y, that's my vertical image. My horizontal image is going to be 1, 0. Again, because of our I and j Cartesian notation, I've gone 1 increment in the x direction, but I've gone no increments in the y direction. Okay. It's very important that we learn how to use these images. So if you put them together, you get a 2 by 2 square matrix rather, and that's basically the box. So if you put them both together, you get a box. But generally, we just use these two individual images by themselves to describe what a matrix is doing. Okay, and I'm going to box that also in red. With a slight note, images help us to describe a transformation. Apologies for my handwriting. So I have a question here that I think would be pretty useful in describing these concepts. And the question is right here. So part A, we're given a matrix R, where A and B are constants, and A is not more than 2. Now, I can already see that the reason why A is not more than 2 is because if A was less than 0. Because if A was 0, then we would have a singular matrix. And I believe singular matrix don't have a determinant, so therefore they don't have a scale factor. They do nothing. Okay. So part A for 3 marks asks us to find R squared in terms of A and B. I think that's quite straightforward. That's just a bit of matrix algebra. So I like to do it this way, where I arrange the matrix like this. So A to A, B. Oh dear. And the other matrix A to A, B. And down here is where I will have my final result. And I'm just gonna detail that just in a box like this. So the way we do it is that we line up where the box is with the columns and the rows, and we do multiplication outwards. Okay, so for this box here, it lines up with this column and that row. So the summation is going to be 2 times A, so that's my first multiplication. Then plus, so we move outwards, plus A times A, which is going to be A squared. So the answer in this box is going to be A squared plus 2A. And using that same method, the answer in this box here is going to be 2a plus 2b. The answer in this box is going to be a squared plus ab. The answer in this box here is going to be b squared plus 2a. And that is our matrix R squared. Okay, very straightforward. Part B tells us that R squared represents an enlargement with center 0, 0 and scale factor 15. Okay, so it's very important to be aware of when the question says this, because that's basically telling us that no matter what we do to the origin, it will never move. It will always remain 0, 0. So it is true that this matrix, this transformation matrix, is just a simple enlargement. How will we describe what this enlargement is doing? Well, we can use images. Well, and we're also going to use images to find out what the values of A and B are. So, as I wrote up here, I have two images. I have my X image and I have my Y image. And these form the unit square of area 1, okay? Because 1 times 1 is 1, yeah? And again, it's very important that I said that because it relates back to the determinant scale factor area, okay? So I'm going to write here, use X or Y images. I'm going to use both because there's something that I want to show, okay? So here I'm going to write using X, which is 1, 0. So I'm going to transform this matrix using this transformation matrix up above, right? And that's going to give me a scale factor of 15. That means this is going to be multiplied by 15, okay? So already I'm going to write, I can write that 1, 0 multiplied by the matrix a squared plus 2a, then 2a plus 2b, b squared plus 2a, a squared plus ab. Down here, I'm going to get 15, 0. Okay? Because going back to the question, it says that R squared represents an enlargement with center 0, 0 and scale factor 15. So I've stretched this by 15. Yeah, I've simply multiplied it by 15. Now the matrix algebra to get 15 and 0 is going to be like so. Again, we move out by multiplying. So it's going to be 2a plus 2b multiplied by 0, which equals 0, plus a squared plus 2a times 1 equals 15. So my top equation is going to be a squared plus 2a equals 15, okay? And I ignored this. I ignored the 2a plus 2b because that multiplied by 0 is 0. I don't need to include it. For the bottom one, it's going to be b squared plus 2a times 0, which is 0, so I ignore that. Then move outwards, so a squared plus ab times 1 gives me 0. So my second equation is going to be a squared plus ab equals 0. Okay, and I'm going to do something special by highlighting this in orange because there's another way which we can get our final answer of A and B by using this and the second one which I'm going to write using the Y image. So using Y, the Y image, which is going to be 0, 1, same concept applies. So 0, 1 multiplied by my transformation matrix R squared, b squared plus 2a, and a squared plus ab is going to give me a stretch in the y direction of 15. And the matrix algebra to get this is going to give me 2a plus 2b equals 0. And then down here, it's going to give me b squared plus 2a equals 15. Because again, a squared plus ab times 0 is just 0. We don't care about it. And the one that equals 0, I'm going to highlight that again, or box that again in orange, because we can use that later on. Okay. Now, there's two ways we can now solve for a and b from this point forward. Remember, I have not used the determinant yet. I will use the determinant later. Here, I'm just going to simply use algebra. Yeah. I can use either the x side or the y side. It doesn't really matter. All I need to do is just solve one, and then solve for one, and then solve for the other. So on the x side, equation 1, I just have a squared plus 2a equals 15. So if I rearrange that, it's going to be a squared plus 2a minus 15 equals 0. This is just a quadratic. And factorizing, I'm going to get a squared plus 5a minus 3a minus 15 equals 0. Take out the common factor. So minus 3a plus 5. Then a plus 5, a. So therefore, I get a minus 3, a plus 5 equals 0. So a equals 3 or a equals 5 as two possible answers. And then when you substitute a equals 3 or a equals 5 into any one of these, you get b. You get b coming out as b equals minus 3 or minus 5. The solution actually says that a equals 3 and b equals minus 3. I'm not going to go far into the elimination cycle of, you know, is b going to be minus 5 or minus 3, or is a going to be 3 or 5? I'm not going to get into that. That's just a couple of lines of just plugging them into the original equations and just seeing which one fits. Okay, so this is using algebra. So a equals 3 and b equals minus 3. I just picked my first answers. How about we use the determinant? Okay, how about we use the determinant? So down here, I'm going to write using the determinant, because there's quite an important concept here. If we were to create the determinant of this matrix here, yeah, again, going up here, the determinant is the diagonal subtracted by the opposing diagonal. So AD minus BC. So it's going to be a squared plus 2a times b squared plus 2a minus 2a plus 2b times a squared plus ab. Yeah? So I am going to write that down. So a squared plus 2a times by 2a plus b squared minus a squared plus ab times by 2a plus 2b. Okay, now what do I equal that to? Well, going up, again, I wrote here that it equals the area scale factor. It's not just simply the scale factor, it's the area scale factor. But what did I write over here? When you put the two images together, you get a unit square. Now the unit square is going to be squared whatever you've stretched in either direction. So if I've stretched the x direction by 15, and if I've stretched the y direction by 15, I'm going to get a total area of 15 squared. Yep. So don't be fooled when the question says that scale factor 15. No, the area scale factor is actually 15 squared, which is 225. 225. That's the area scale factor. If you were to turn the images into a unit square, the area scale factor is actually 15 squared, which is 225. Okay. Now, we've still got too many constants here. I mean, too many unknowns here, a and b. We can only solve for one at a time. So let's come back here. These orange boxed ones still hold true. Either 2a plus 2b equals 0 or a squared plus ab equals 0. Either one is fine. I'm going to go with the 2a plus 2b equals 0. Okay, and this comes from the fact that when you do the transformation on the images, one of them is going to equal 0. That's just a fact of the mathematics. Okay, so I'm going to write 2a plus 2b equals 0, and that is automatically going to bring this whole part of the equation here to 0. And then I still got some unknowns here. I want to get rid of the b, so I'm going to rearrange for the b, make b the subject, and just say that b equals minus a, and then substitute that into there and remind myself that that equals 0 because 2a plus 2b equals 0. So this whole thing goes to 0. Yep. So I'm left with a squared plus 2a multiplied by 2a plus a squared, because minus a squared is going to be a squared, minus 225 equals 0, because I brought this over. Okay, now this is going to give me a quartic. So if I just multiply that out, I'm going to get something like a to the 4 times, I think, 4a cubed plus 4a squared. And I am going to make sure that that is correct by doing it in grid style. So a to the 4, 2a cubed, 2a cubed, and 4a squared. Add them all together, so this is correct. Okay. Now I'm not gonna go through the whole how do you factorize quartics. I'm just gonna go straight onto Desmos graphing calculator. Yeah, I'm just gonna go straight onto Desmos graphing calculator and just type this whole expression into the graphing calculator. Okay, so we have x to the power 4 minus 4x cubed plus 4x squared minus 225. And if we zoom in, we get our solutions as x can either be minus 3 or x can be 5. And from the solutions that I'm looking at, one of the answer is actually one of the variables is x equals minus 3. Oh, sorry, I made a mistake here. That's meant to be, so that should show up better, yeah. So if the x was a, then one of the solutions of a would be 3, not minus 3.